I'm Dmitry Duplyakin, and in the next 20 minutes, I will tell you all things related to avoiding the order entrap in systems performance measurement. Let me start with a quick story. This was a couple years back when we were working on a different paper for OSDI. That paper was titled Taming Performance Variability. We were benchmarking memory performance, and we saw with Stream something interesting where the performance for the newer servers that we had was 3 times worse than the performance from the older servers. Not particularly great, and we needed to investigate that. It turns out that this had to do with how the memory pages were allocated, and in particular how it was happening on the on the servers with the unbalanced DIMM configuration. So a very specific example, but what we learned here as well is the fact that if we were to run some CPU tests, it didn't really matter what tests those were, as long as they allocated and used a lot of memory, we would see memory, like performance recovery. We would get the 3x back and see totally expected results. So kind of interesting, kind of odd, but what we learned here is that the order of benchmark execution may affect the results, and in some cases it could be pretty significant. So again, pretty remarkable, pretty interesting finding, kind of within its own case, but we decided to sort of study this type of phenomenon more broadly. So here it is. It's possible that an experimenter runs some tests and learns that system A is better than system B with respect to a particular performance metric. It could be a runtime, latency, bandwidth, or a similar metric. Well, it turns out that it may or may not hold true if the following holds. If A was always tested before B and A tests systematically impact B tests. Clearly, that's a problem here. This is sort of a flawed setting, but if we see that scenario in action or not, well, we need to sort of be careful not to kind of follow this sequence. Well, let's step through it one more time. So here's how it works in our opinion. It starts with this assumption. So we can't assume that results obtained from individual performance experiments are independent. It may or may not be true, but that's sort of underlying assumption here. It causes us to run the tests in any order, basically without paying attention to the order effects. And then in the end, we get the incorrect or unreliable conclusions. We can also call them biased conclusions, where the ordering becomes the biasing factor. And again, next time we run it in a different order, maybe we get different conclusions. Again, hopefully for most of the experiments, it's not an issue, but for some it could be. All right, so at this point, one may wonder, what are the root causes? What's causing this weird behavior? Well, the root causes here relate to performance affecting system states that change or stay the same across the experiments. And of course, we can all think of the caches, data layout in RAM and disk. Well, it turns out there's a longer list of these things. They're sort of behind the scenes factors, and they're all sort of create this trap, right? You may or may not pay attention to them. You may or may not fix them. You may not sort of monitor them. They may be totally outside of your control. A lot of these things are good for performance reasons, like performance optimization reasons. But of course, if you keep running your experiments and change certain things and order changes from underneath you, well, then you can get wrong or different conclusions. So I've got to pay attention. And then here's my early version of key takeaways slide on how to avoid the order entrap. Well, you need a couple of things. You need a relevant reset to clean state procedure. It's clearly well, it depends on what you're testing, right? Depending on the application or system you're testing, it could be a reboot of the machine if you're really trying to be careful. Maybe it doesn't need to be that involved. Maybe you just start and restart the service you're testing. Maybe you do some warm-up runs, clear the caches, etc. Once you have that, you ideally want to run experiments in the baseline order, in multiple random orders, and compare the two, right? So this baseline order, something I'm going to refer to as fixed order throughout the rest of my talk. It doesn't mean it's ideal sequence, it's ideal order, but it's something that is more natural to you or the application you're testing. Oftentimes, if we see something like buffer size, it could be that experiments go from lowest buffer size, from the smallest one to the largest one. Sort of that's how we like to code things. But again, hopefully this baseline order represents the practical settings for your system. And then when we have enough data, then we should compare results using statistical tests. All right, and here's the outline of the rest of my talk. I'll cover 4 pieces with the survey, with the methodology we developed. I'll introduce this long-term performance data set we collected and analyzed, and I'll end with the description of a tool and 3 case studies. All right, let's dive right into it with a survey. It was our overall impression that in the literature, we don't see too many studies talking about this particular effect, this ordering performance issue. Well, we wanted to sort of be scientific about it and prove it or disprove it. And for that, we designed this survey where we started with 130 papers that were recently published, were presented at OSDI, SOSP, and EUROSYS. So kind of these 3 conferences represent the computer systems research. And with this survey, we filtered it down to 56 papers that all had the functional and reproduced artifacts and were considered in scope for this survey. So that's kind of our final set that we reviewed. So it turns out we were totally right with that impression. Very few of these papers, around 7%, really specified how they ran the experiments and discussed what we consider the inner experiment reset procedures. It was clearly stated how they did those things. Well, there is a gap there, and we're hoping with our work we move the needle in the right direction for addressing this gap. With artifacts, we saw something different and also remarkable. We were looking specifically for a randomized experiment design, right, where tests run in random orders, and it turns out these particular studies did not really follow that. And again, seems like an oversight, but it's possible that people considered that and just not included in their final work. That could be the case, but still something to pay attention to kind of, with the ordering issue. All right, with the methodology, I'm gonna dive right into it now, and I'll start with the terminology. So by a test in our work, we call an individual benchmark, and we follow the approach where one benchmark returns one numerical value. That's one result. With a trial, trial means the execution of a test, and then with the run and experiment, we sort of aggregate these things. Run is a set of trials. It could be a fixed order run or a random order run, and then with the experiment, we have multiple runs. All right, in our methodology, we have essentially 4 parts. First, an experimenter needs to define this baseline order. I already mentioned that. Then there should be a notion of this reset to clean state procedure. It should be defined and implemented and used. Under piece 3 here, step 3, we have execution of both fixed and random orders and repetition for each. You see a visual representation of that on the right for n equals 3. Again, just one of the possible sequence of these fixed and order runs. And finally, once we run these types of experiments, we complete these runs, we need to run the statistical analysis. We suggest something called Kruskal-Wallis test. It's a good non-parametric test that allows us to tell whether samples come from the same distribution or not. Mann-Whitney is a good alternative here. But I do want to warn you, we shouldn't use the parametric tests unless we're certain that the performance results we're studying nicely follow the Gaussian distribution, which is not always the case with the performance results. It's usually the opposite. So non-parametric tests are best here. And then we use in our work something called Bonferroni correction. That's important for doing multiple comparisons. Well, it turns out if you follow this procedure, you can arrive at 2 conclusions here. First, if any of the tests' p-values run below this threshold, then the order of the test matters. Alternatively, if all of the tests return p-values that are greater than that threshold, the order likely does not matter. Again, we're just using sort of the statistical set of tests and then interpret the results here kind of for the overall experiment and for individual tests we're running. All right, now one may ask, well, how different are the results, right? So technically speaking, statistical tests can tell us that the results are different in statistical sense, but but the differences may still be fairly small. So we're trying to assess that here, the magnitude of the effect, and we can do something very simple. We can measure relative difference, express it in percents. So that's the difference of means divided by one of them times 100. I'll show you examples of this metric in my following slides. And visually, in kind of different, like using a different concept here, we can draw medians and confidence intervals. We can kind of express our findings in this way. In the red flag case here, case 1 is the one where confidence intervals don't overlap for the results that we see. Therefore, we sort of see non-conforming results. And if we report either fixed order runs or the random order runs, we can have different they represent different ranges and we can arrive at different conclusions. So that's something to be careful about. All right, well, with that methodology, I'm just going to dive into the analysis of this long-term data set that we collected. Very briefly, how it was collected. So we used the Cloud Lab testbed to collect a large volume of results, over 2 million trials coming from 9,000 runs. What's important here is that we used low-level, we used micro-benchmarks to assess memory performance and CPU performance, and these were truly independent runs. Each run started after a fresh reboot. So that's as best as we can do to kind of gather this kind of data set with independent runs. All right, in the next couple of slides, I'll show a sequence of plots where each point represents a comparison between a set of random order runs and then fixed order runs. Again, they're kind of matching and comparable results, and the only difference is the order. So we're trying to kind of distill the importance of that factor. Well, for the points that fall below these purple lines, we can tell that the order matters because that's what these tests tell us. And overall, statistically significant effects due to ordering are found for the majority of these cases and for this overall experiment. So this sort of confirmed our intuition that the order is important, but now we're going to assess like how big is the difference. So it turns out that these ordering effects can be quite large, up to tens of percents. So again, nothing else changed, the same hardware, same tests, and just the order is the difference. The mean absolute percentages here are at 8 and 7.3%. So something to be said here about the practical importance of this. Of course, if you're reporting on a system and on multiple systems and system A is better than system B by a large margin, maybe these effects are not relevant. But if that margin isn't that great, you have to kind of pay attention to how each of those systems is studied. So that's kind of the bottom line here. All right, so different cases for overlapping or non-overlapping confidence intervals. Case 1 is the one dominating here. So it's a red flag type of situation here. So non-overlapping confidence intervals show up a lot in this set. Putting it all together, we conclude that rigorous performance analysis must consider order of test execution, and that should lead you to more accurate conclusions. All right, and finally, the last piece. Well, this methodology was proved useful in this analysis that I presented, and then we decided to implement a tool that follows it and helps you orchestrate these steps and these runs. We called it OrderSage, as in Order Smart, and it's available at this link. This tool is capable of using any repository that you may have for your experiments where you run your individual tests in a fixed order, and this tool will shuffle it, run it again, collect the results, and perform the analysis. All right, under the case studies, we looked at 3 different things. I won't get into the details. I'll encourage you to read the paper. But I will say that for all 3 of them, we concluded that the order of tests matters. In one case, the second case here, that the largest percent difference is very small. It's under 1%. So it's not a huge issue here, but I will mention that for the other 2, it's actually much larger, 5% and almost 17% for the third case. Actually, for that case, I will say that this is an artifact that we used from SOSP paper on UFS. And even though our work reproduced the results from that paper, and the conclusion holds. It's still important to remember that the percent delta is, percent difference here is very large. It just turns out that that paper reported much larger improvement from the base case, from the base system, and this didn't come into play with the conclusion. But still, it's important how both baseline and the presented system is studied because we see such a large delta there. So 17% is non-negligible. And at this point, here's my last sort of takeaway slide. So avoid the ordering trap, pay attention to the order of execution, follow the methodology and the tool we presented. Hopefully they move the needle in the right direction. All right, we released the artifact with the code for this tool and the dataset we collected. And that's it for my talk. Thank you. I'll take questions, including the ones I listed here for convenience, but of course you can ask your own questions too. But no judgment with the questions. Thank you.